So this is topic 9, starting with inorganic chemistry. This is the first video in the series of lectures to be recorded for inorganic chemistry. We start with 9.1, which is physical properties of the elements in period 3. So topic 9.1, physical properties of elements in period 3. Okay. Period 3 is row 3 of the periodic table. Okay, there are 8 elements in the period. We start with element number 11, which is sodium. Then there is magnesium, there is aluminum, silicon, phosphorus, sulfur, chlorine, and argon. Atomic numbers 11 through 18, that's the entire period. Okay. So what we are going to do is we're going to talk about something called as periodicity. Okay. Something called as periodicity. The term periodicity refers to the variation or the gradual trend, okay, seen in the physical and chemical properties. Okay? You find that there is a gradual change, there's a gradual variation in the physical and chemical properties of elements. You find periodicity across the period. You also find periodicity down a group. But our discussion today deals with the periodicity in period 3. Okay, and the first thing that we need to talk about is the atomic radius. All right, let's talk about variation in atomic radius. Okay, in the previous version of your data booklet, we had information about the atomic radius of the different atoms, so that would have been helpful. But even otherwise, I think they just expect you to know it qualitatively without looking at data. And the fact remains that the atomic radius, okay, decreases across the period. So the atoms get smaller as we go across the period. Okay. So sodium atom happens to be the smallest, and the atoms decrease in size till chlorine. And then argon increases, but argon is a little bit of an anomaly for 2 reasons. One is the fact that it's got a complete outermost shell, and also its atomic radius is measured slightly differently compared to the other guys, considering that it's a noble gas, it stands alone. So the measurement of the atomic radius itself is different. So that brings us to the question, why do the atoms become smaller as we go across the period? That's because atomic radius is the distance between the nucleus and the valence shell of an atom. So it's the distance from the nucleus, which is the center, to the outermost electron, because where the outermost electron is present is the valence shell, it's the valence electron. All right. But what varies? You find that as we go across a period, the number of protons increases. Okay. As we go across a period, the number of protons increases. So the nucleus is going to become more and more positive. All right. So more and more positive. So as you go across a period, the number of protons increases, hence nuclear charge increases. But remember, the electrons, when they are added, okay, from sodium is 11. So magnesium has got 1 extra, aluminum has got 1 more extra, silicon has got 1 more extra, so on and so forth. But when these electrons are added, these electrons are being added to the same shell, which means it has got only 3 shells. So the shielding effect remains fairly constant. So shielding effect does not play a part. All right. As the electrons are added to the same valence shell, the shielding effect remains fairly constant. So the nuclear attraction for the valence electron increases. So what happens is, so as we go across the period, the nucleus seems to attract the electron even more strongly. So let's say that's your nucleus, okay? And say this is your valence shell, okay? This is your valence shell. Now, so this is your valence electron, all right? So this is your valence electron. Now this nucleus is positive. It attracts this electron, okay? But because of this attraction, if the attraction is strong, this electron is pulled a little closer. So from there, it moves a little closer. So this electron is going to move from there to say a little closer. Remember, there is no shell physically. The shell is the region of space where the electron is, which means if the electron has been brought closer, it means the shell is also brought closer. Okay, the shell is also brought closer. And that basically means the atomic radius, which is the distance between the nucleus and the valence shell, is also decreased. And hence, as you go across the period, you find that, okay, the size of the atom decreases. So as the nuclear attraction for the valence electron increases, okay, across the period, the valence electron is attracted most strongly, okay, and is pulled in. This decreases the distance between the nucleus and the valence shell. So atomic radius, okay, atomic radius decreases across the period. Now, the okay, as far as the AS chemistry is concerned, we just say that argon has a complete outermost shell and hence is able to overcome or escape nuclear attraction. Because if you keep the trend, argon has got the most number of protons in this period, 18, which means the valence electrons of argon need to be the ones that are very strongly attracted and hence maximum pulled in. But we would say that argon has a complete outermost shell and hence able to overcome the nuclear attraction. Hence, its atomic radius is the largest in period 3. Okay, the largest in period 3. However, the truth of the matter is, this whole idea of atomic radius isn't exactly measured in the same way. And the reason has to be because of the bonding. Sodium, magnesium, aluminum are metals. You basically have metal cations surrounded by delocalized electrons. While silicon is a macromolecular structure, similar to diamond, it's covalently bonded. While, say, phosphorus, sulfur, chlorine are covalently bonded, P4SHCl2 molecules held together by van der Waals forces, okay, ID-ID interactions. While argon is monatomic, held to totally only by ID-ID interactions. So the way the radius is measured and defined for all these itself is different. And while at least for the metals, okay, sodium, magnesium, aluminum, till up to chlorine, okay, the covalent ones, it's comparable, okay, you find that the argon case is entirely different and hence you find its radius, okay, as reported is pretty high, okay, that's the reason. Another thing is usually they'll ask you to explain the trend. Sometimes they do ask you to draw the graph to represent it. So this is just a simple shape graph. Okay, so you are going to plot the atomic radius, okay, against the elements. So let's say there's sodium, magnesium, going up to say chlorine, and say this is argon. All right, I haven't listed the other ones. Okay, you find that from sodium down to chlorine, it decreases. I'm only drawing a trend line. I'm not telling you that it's gonna change this linearly and it's gonna just be a straight line. Okay, and from chlorine to argon is actually bigger. In fact, argon is bigger than, slightly bigger than sodium itself. So please make sure that that is okay.